Anyone respond?
Yes, sir, you are audible.
Yeah, thank you. So in the last class, we talked about three different classes of higher order systems. We are going to discuss, and these are the three types of systems. First one is in first order processes in series, that we have already discussed in the last class. Second topic is processes with date time. This is also covered yesterday. And what is left? That is processes with inverse response. Okay, so this third topic we want to cover today, processes with inverse response. This is our third topic that we want to cover today. Okay, now to study this, to know this inverse response, we would like to adopt one example. So here we have taken a boiler. You draw the schematic of this boiler. Then we'll discuss about this inverse response. So in this boiler, basically cold water is fed and heat is introduced. Then the cold water evaporates and steam is produced. So this is the basic concept of a boiler that you, I think, know everyone. I repeat, you see, cold water is fed to a boiler. This is the level of the cold water. Then we are introducing heat, and that amount we have expressed by capital Q. Then naturally the water evaporates. In fact, water is converted to steam, a fraction of the water. And then that steam is taken out at the top as the product of this boiler. Now we are considering, you see, a situation where this horizontal line is basically indicating the steady state, or it's a fixed value of Fi. Then suddenly we are increasing the flow rate of this cold water with a step change. It's a step increase basically. Okay. In the right hand side, it is shown that initially the Fi was fixed, which is indicated by this horizontal line. Then at a certain time period, we have increased the Fi. It's basically a step increase. Now, what will happen in terms of height? Can anyone give the answer? Initially, the process or boiler is at steady state condition. So that is indicated in fact through this horizontal line, which is also true for Fi. Then at a particular time instant, we are increasing this Fi. We have considered a step increase in Fi. Can anyone give the answer? Because of this, what will happen in terms of height in the boiler? Water height in the boiler? Any answer, student?
It will increase.
Which one?
Height.
Height. Okay. Now let us come to the consequence. This is the overall consequence, you see. If we increase Fi by a step, that means there is a step increase in Fi. Then at the beginning, height decreases. Definitely for a short period of time. and then it starts increasing consistently. If we increase the inflow rate of water, that's a step increase. Initially, the height decreases for a short period of time, and then the height again starts increasing consistently. Now, question is how it happens. So this is the first thing. For a short period of time, how height is getting decreased. So there are basically two time periods. In the first time duration, there is a decrease of height. In the second time duration, there is an increase of height. I repeat, in the first time duration, there is a decrease of height. And in the second time duration, there is an increase of height. Now, in the first time duration, how height decreases, that is written under this first point. If Fi increases, time decreases. If Fi increases, temperature decreases. And decreasing temperature leads to decrease the volume of the entrained vapor bubbles. So naturally, the differential pressure cell, which is measuring the liquid height, it gives lower value for H. Okay. And this dynamic change in liquid height in the first time duration is explained by this first order transfer function. This is explained by this first order transfer function. It is seen through the experimental investigation that it looks like the response of first order transfer function that is indicated here. You see negative sign you are understanding because it is decreasing. Now come to the second time duration. I mentioned in the second time duration there is a consistent increase of liquid height. In the second time duration, I mentioned that there is a consistent increase of height. Now how it is indicated by this point 2, you see. We are not changing our heat input rate. We are not changing our heat duty to the boiler. So if heat duty is constant, then definitely, the steam production remains constant. But we have already increased the Fi, so height will consistently increase. I repeat, our heat duty is not changed because of the increase of Fi. Okay, that heat duty we have kept constant. That means our production or evaporation rate remains constant. But Fi has already increased, so height will naturally keep on increasing. Height will keep on increasing with time consistently. And that is explained by the response of this function K2 by S. Okay. Now let us combine these two. This is a block diagram. Our input is Fi, our output is H. And there are two types of response involved in this boiler system. One is first order response, which has negative sign. Another one is K2 by S, which carries positive sign. This is the block diagram. In this block diagram, you see Fi is our input and liquid height H is our output. And as discussed, there are two transfer functions. For the first time duration, we have a first order response. So it is K1 divided by tau 1 is plus 1, which carries negative sign. And in the second time duration, we have K2 by S and it has positive sign. So this is the overall H we get by combining these two. Fine. This is the block diagram. Now come to the graphical representation. If we come to the graphical representation, it looks like this. You draw this figure. This is the graphical representation between liquid height versus time t. Why is liquid height here? This is the graphical representation between liquid height, that is y, versus time t for the boiler system. Okay, so you see this is first one, that means first order response. K1 divided by tau 1 is plus 1. And this second one is basically K2 by S. So if we combine these two with time, we'll get the overall response like this. This red color basically the combination of first and second response. So are you understanding why this is called inverse response? Why? From this graphical representation, can we extract any comment? Why it is inverse response? Anyone? You got my question? Our title is, dynamic response of, dynamic inverse response of a system. So from this graphical representation, are you understanding why it is called the inverse response? Any student? Yes.
So because initially the response is in opposite direction.
Yes. Initially, it is just going in reverse direction. You see, it is decreasing, but after that, it is increasing. That's why the inverse response term is involved. I repeat, initially it is going in opposite direction. And after that, it is moving, you see, up. Initially it is down, then it is up. So that's why it is called inverse response. So it is basically the result of two opposing effects. It is the result of two opposing effects. Okay, that's why it is called inverse response. Now question is, what is the condition for this inverse response? How you can know that a transfer function is going to, respond like this? Answer is here. If you, based on the block diagram, we can write this overall transfer function. This is our transfer function, output y divided by input f. Basically, this is y h by fi. This is h by fi. So you see, this is again the ratio of two polynomials. This transfer function is the ratio of two polynomials. I mentioned before that if we consider this numerator is equal to 0, we get the roots which are called zeros of the system. If we consider this denominator equal to 0, we get the roots, and those roots are called poles of the system. I repeat, it is basically the ratio of two polynomials. One is in the numerator, you see this one. Another one is in the denominator. If we consider this numerator term equal to 0, we get the roots. Those roots are called zeros of the system. Similarly, if we consider the denominator equal to 0, we get the roots. Those roots are called poles of the system. Now you see, this is the condition for inverse response. The system must have positive 0. If a system has positive 0, then we will have inverse response. Now, how we can get positive 0? If Q1 is greater than K2 tau 1. Fine. I repeat, if a system has positive 0, then it should show the inverse response. Now, for this particular example, we can have positive 0 only if K1 is greater than K2 tau 1. If this is not satisfied, there is no existence of inverse response. Yeah, do you have any question on this? Inverse response? Student? Okay, fine. So I think you understood this. Now, one question is that how we can tackle this situation. You see, it is degrading the performance, particularly at this initial stage. Our height is moving in opposite direction. The question is how we can tackle this situation. We'll discuss later. Like just our last topic was processes with date time. So date time also, hampers the process response. Similarly, this inverse response also degrades the process response. Okay, so natural question is how we can tackle these situations. We'll discuss this issue later. Okay, let us a little more matured in process control, then we'll come back to these topics again. So our next topic is introduction to feedback control. Our next topic is introduction to feedback control. At the very early stage of this course, I have highlighted different kinds of controllers like feedback controller, feed forward controller. Anything else I have highlighted? Inferential controller. Okay. At the very early stage of this course, we have briefly started through a couple of examples like feedback control, feed forward control. Those control schemes now we want to study in details. So let us start with this feedback control scheme. Now to discuss this feedback control scheme, first we want to know how we can develop the block diagram for a process with feedback controller. At first we want to know how to develop the block diagram for a process with feedback control scheme. That is our first topic of discussion under this title. So let us adopt this heating tank system, which we have considered several times before. You draw the schematic of this heating tank system, then we'll discuss how to develop the block diagram. So this is a heating tank system, and I hope you all are accustomed with this system. Here Fi is the flow rate and Ti is the temperature of the inlet stream, and their corresponding flow rate and temperature for the outlet stream we are representing by capital F and T. Okay, steam is there, which is basically supplying heat. And for this heating tank system, our control objective is to maintain the temperature at its set point value. That's why it is written here as T equal to T set point. Now for this example system, our control variable is selected temperature, because I have mentioned before that if you fix this control objective, that variable is basically selected as control variable. Manipulated variable here is steam flow rate, and our load variable is Ti. There are basically two load variables, Fi and Ti, but if you see the next line, I have clearly mentioned here that Fi and F, those two variables are constant and equal. So accordingly, we have only one load variable, that is Ti. Okay. Now, if these two flow rates, inlet and outlet flow rates, they're identical and constant, then there is no variation of liquid height in the tank. So this is our open loop process. Okay. This is our open loop process. Why it is open loop? Abbas Sarkar, 10001. Can you respond, Abbas? Why this is called open loop process? Do you have answer?
No, sir, I'm sorry.
Okay, next one, Kunjaravi Kiran.
Sir, because it is not having that sensor part, I mean that sensor and configuration, that configuration part, sir.
Control configuration is
Yeah,
not.
yes, sir.
Yes, yes, correct. So straightforward answer is there is no controller. Okay, so this is open loop process. Now let us employ the control scheme. Basically, we want to develop the closed loop process. You see, we have the same process heating tank system, but we have included our control configuration. Draw this figure. Just you include the control configuration part. So one thing you see here, our actual temperature we are representing by capital T, but after measurement we are representing that temperature by capital T suffix M. In practice they are not identical, but sometimes we assume that they both are identical. Okay, because sensor has certain measurement errors. I repeat, actual temperature we are representing here by capital T, but after measurement we are representing that temperature by T suffix M. Reason is the temperature sensor has certain measurement errors. So in practice they are not identical, but theoretically we sometimes assume that they both are identical. Okay, so this is the closed loop process, heating tank system plus the controller or control configuration you can say. Now based on this figure, we want to develop the block diagram. This is the block diagram. See, you start like this way, then you can easily, understand it. First, you draw this process block diagram. See what I am saying, you follow like this way. You first draw this process block. This is a process block. First draw this process block. Okay. Now what are the inputs to the process? There are two kinds of input. One is the disturbance, another one is the manipulated variable. So in the second step, you connect these two inputs. One is disturbance, that is Ti, and second one is manipulated variable, that is M. Fine. I repeat, whenever you are going to draw this block diagram, especially at this beginning stage, you start with first including this process block in your page. First you draw this process. So this process has two inputs. You know inputs are input variable, that is two types. One is disturbance variable, another one is manipulated variable. So in the next step you include these two inputs. One is Ti, another one is M. Now what is the output of this process? Temperature. So you just include this arrow which is coming out from the process block, and this is basically the temperature. Temperature is the process output. Then what we are doing? We are measuring this temperature. So you draw this measuring sensor and this line. We are first measuring the temperature T, employing one sensor. So you draw this part, measuring sensor, output is Tm, and it is going to the comparator. Okay, so first you draw the process, connect its input and output. Output is temperature. We are measuring the temperature in the next step, employing one sensor, and sensor output is Tm. This Tm is subsequently compared in a comparator with its set point value. So this is set point, this is measured temperature. What is the output of this comparator? Error signal, epsilon, you see. Where this epsilon is going? It is going to the controller. Next, you draw this controller block. What is the controller output? C. This controller output is going to final control element, FCE. That is nothing but a control valve. And then it is giving the manipulated variable, or it is implementing the manipulated variable. I repeat the block diagram. You first draw this process, connect its inputs and outputs. Here output is temperature. Then at first we are measuring this temperature. So you employ one sensor to measure the temperature. What is the sensor output? Tm. That Tm is going to compared with its set point value. This is the comparator. Comparator output is error signal. This is error signal. It is going to the controller. This is the controller block. Controller output is basically implemented through the final control element. This is the final control element, which is nothing but a control valve. And naturally that is going to implement the manipulated variable. Just one correction in this block diagram. FST, it should be placed here. FST is manipulated variable. You just replace, you remove the FST from here and you write here FST. Got? FST is not C. FST is basically manipulated variable. So you just place here FST. So you understood this, or if you have any question, you can ask me, or if you have any doubt. So I hope it is clear to everyone. Okay. Now let us come to the types of feedback controller. You see in this last block diagram, we have this controller block. Let us come to discuss the types of feedback controller. And in the last block diagram, figure 3, we have this controller block. Controller input is error signal, epsilon, and output is C. Fine. We have a controller block, and input to the controller is the error signal, and output from the controller is basically C. So controller is relating C and error signal. Fine. If this you consider as a transfer function, then C by error is this controller transfer function. Now various types of feedback controllers differ in the way they relate epsilon t to Ct in time domain. Various types of continuous feedback controllers differ in the way they relate error to C. Let us see how they relate, but before that, let us know the three types of control actions. There are three basic types of feedback controllers. One is proportional only, proportional integral or PI, and proportional integral derivative or PID. There are three basic types of feedback controllers. First one is the proportional or P only controller. Second one is the proportional integral or PI controller. And third one is the proportional integral derivative or PID controller. So these are the three basic control schemes. Now you see there are basically three control actions. One is proportional action, one is integral action, one is derivative action. If you see the three basic control schemes, there are three control actions. One is proportional action, which is present in the first type. One is integral action. Third one is derivative action. Okay. Now in the first type, only proportional action is involved. In the second type, PI, proportional and integral, two actions are involved. In the third type, PID controller, here three actions are involved. You see, proportional, integral, derivative. So similarly, we can combine also proportional and derivative two actions, which can give us PD controller. We can also include integral and derivative action, which can give us ID controllers. Okay, so these are also the options. Okay, let us start with this P only controller, proportional only controller. It is saying that the output is proportional to the input. Let us start with proportional controller. So proportional means here output signal C is proportional to the input signal error. You see in this equation it is indicated. Output signal C is proportional to the error signal. That's why it is proportional controller. And here C prime and error epsilon, both are deviation variable. So from equation 1, we can write easily equation 2. Basically, you write like this way, C prime equal to Kc epsilon. Then you write equation 2. For better understanding, you write after equation 1, C prime equal to Kc into epsilon. Then you write equation 2. C prime, you know, C minus Cs is C prime. Okay. Now you see there are two additional terms involved in equation 2. One is Cs, another one is Kc. Compared to equation 1, equation 2 involves two additional terms. One is Cs, another one is Kc. Kc is called proportional gain. Roll number 10030, Pooja Sharma. Are you there? Pooja Sharma, 10030.
Yes, yes.
You tell, what is the definition of, general definition of gain? Any idea? Any way can we express the gain term? Yes or no? RJ Reddy?
Sir,
Yeah.
gain is maybe
Yes.
like the output which we are getting in
Tell, you are in correct way.
the output which we are getting with respect to the input.
Yes. So it is written there, you see, change in output by change in input.
Yeah, yes, yes.
Yeah, correct. So gain is basically, the general definition of gain is change in output by change in input. Okay. So why the gain term is involved here, we are understanding. Now proportional, you know, this gain is involved with the proportional controller. That's why this term is there. I repeat, the general definition of gain is, it is basically, I mean, we want to represent by gain, that is change in output by change in input. So that's why gain term is present here. And since it is involved with the proportional controller, that's why this proportional term is also involved. So Kc equal to this we are getting. You see, we can easily get from equation 2. Kc equal to C prime by error, we can get from equation 2. So it is nothing but change in output by change in input. So what is CS? How to define CS? Can anyone tell? You can give the answer from equation 2 only. How we can define CS?
Steady state value of C.
Yeah, better, I mean, other way from equation 2.
So it's the bias signal.
No, that's fine. When C equal to CS. Both answers are correct. I'm not saying wrong.
When
T
epsilon
equals
is
to
0.
0.
And epsilon equal to 0. Yeah, T equal to 0. Yeah, if at T equal to 0 we have steady state, then it's fine. So CS equal to basically controller's bias signal. One of your friends told. This is correct. This is steady state value of CT. From equation 2, it is obvious that C equal to CS and error equal to 0. Fine. When epsilon equal to 0, we have C equal to CS. So usually at the beginning, we consider our process is at steady state. Accordingly, we can say that at the beginning or steady state, the C is basically CS. So this Kc is basically the tuning parameter. You can note down also this point. This Kc is, or proportional gain is, tuning parameter. This tuning parameter you need to determine and include in your computer program. Kc is the tuning parameter which you need to determine and use that value in your computer program. Okay. Now you will see that in many softwares, control oriented softwares, they use proportional band PB instead of Kc as tuning parameter. There are few softwares which use an equivalent term of Kc called proportional band, and that is expressed by this. Proportional band is 100 divided by Kc. And its typical value is in between 1 and 500. Fine. But we hope that this is not true all the times in between 1 and 500. But for the time being, yeah, you note down this. We'll see whether it is true or not later. So what is basically this? If you consider here Kc as delta output by delta input, so proportional band is basically 100 into delta input by delta output. I repeat, if you substitute in place of Kc delta output by delta input, then we'll have proportional band equal to 100 into delta input divided by delta output. So accordingly, this statement we can make. Okay. One next point is finding of transfer function of the P-only controller. Finding the transfer function of P-only controller. Can anyone tell me what is the transfer function of P-only controller? Transfer function, you just recall, it is the output by input. That means C bar prime S divided by epsilon within bracket S. Transfer function is the output by input in Laplace domain. That means C prime bar divided by epsilon bar. What is the expression? Anyone? Transfer function is output by input. So for P-only controller, it is C bar prime divided by epsilon bar in Laplace domain. Anyone? What is the transfer function? Student? Okay. This is the transfer function of P-only controller. This is a transfer function of P-only controller. You see, if we take the Laplace transform of equation 1, we get this form, and output by input, that is Kc. Fine. So this is the transfer function for P-only controller, that is Kc.
Sir, why we don't use the equation to take Laplace transform and find transfer function?
Yeah, if you take, you can take also equation 2, but transfer function is in terms of deviation variable. You see, if you use equation 2, you have to write Ct minus Cs, that is C prime, and epsilon is deviation variable. So you cannot consider C and epsilon together because C is not deviation variable, epsilon is deviation variable.
Okay, sir. Okay.
Okay, so this is the transfer function for our P-only controller. Next, let us make a couple of remarks on this P-only controller. So this is your first remark that we already discussed. proportional gain Kc equal to C prime by epsilon. That is change in output by change in input. They are deviation variable. That's why we have written here change. Now you see the second remark. With the increase of Kc, controller becomes more sensitive to error signal. Our second remark is with the increase of Kc, the controller becomes more sensitive to error signal. Fine, your understanding here, this is the error signal which is, representing the deviation between YSP and Y. So if you take large value, it is more sensitive to error signal. I think there is no difficulty to understand this point. Now you see the third point. Speed of response gets improved at the expense of larger deviations, particularly at the starting time. Speed of response gets improved. I mean, we can get better response, but at the expense of larger deviation, particularly at the starting time. Okay, so let us see through the plot how it looks like. This is the response. We draw this figure. So this red dot line here, you see, this is basically the set point. You write here YSP. Student, you write here Y suffix SP here. Okay, so this red dot line, this one is basically our Y set point. You write here Y set point. So I think you are understanding the third point. We can get better speed because you see it is reaching the set point value faster. This plot, which corresponds to Kc1, reaches the set point value faster than the other two curves. This is because Kc1 is the largest one. Fine. This third statement indicates this. Speed of response means you can say our rise time is less or rise time is the lowest for the largest Kc. And you see, I have written here another term that is offset. Offset is basically the steady state error. Offset is basically the steady state error. So as I mentioned, this is a set point. Fine, this is a set point. But you see, for Kc2, we are having certain deviation here. So this deviation, this one is also offset, and this one is also offset. Okay. This is, I repeat, this is the set point value. So if you see the response corresponding to KC2, it is getting settled with a certain deviation with the set point. So this deviation is also offset, and this one is also offset. In fact, for KC1 also we will have certain offset, but this is very smallest one. Okay, so this is offset. In fact, we will discuss this offset issue later. Okay, you take 5 minutes leave, then we will again come back. Okay, so let us continue our discussion on this P-only controller. Now come to the fourth point. This is the fourth point. P-only controller does not eliminate offset. See, if you are not understanding any point, let me know. I'll discuss, elaborate. If you are not understanding any point, immediately let me know. I will elaborate that issue. Okay. So this is the fourth point. Proportional controller does not eliminate offset. So you need to note down this point. I will elaborate this issue a little later. But for the time being, you just note down this fourth point. I will elaborate this issue a little later. Proportional controller does not eliminate offset. Now you come to the fifth point. How the proportional controller behavior or response looks like. As I mentioned, fourth point you just note down, and I will elaborate this fourth point a little later. Now come to the fifth point. In this fifth point, you see the behavior of proportional controller is shown. You just recall equation 2, and based on equation 2, this graph is produced. This plot is produced. You just revisit equation 2. Based on that, this plot is produced. This plot is produced based on equation 2, that is the proportional integral controller equation. When this error is 0, we have CS. You just put here 0, here. At the origin you put 0. It indicates when error is 0, we have C equal to CS. Okay, student, you just put here 0. At the origin, epsilon is 0, so then we can easily understand that when error is 0, our C is CS. When error is positive, we are moving upward. When error is negative, we are moving downward with the slope Kc. Can anyone tell what is Cmax and what is Cmin in practice? Can anyone give the answer what is basically Cmax and Cmin in practice? 10035 RJ Reddy, are you there? RJ Reddy. 10029 Praneeth. 10029 Pogula Praneeth. 10024 Muskan Jain. Are you there, Muskan? 10024. 10049 Salini. Are you there? Salini 10049. Anyone can give the answer? What is Cmin and Cmax in practice?
The maximum and minimum of our actuator.
Yes. What's your roll number?
19CH30015.
Rohit. It's better to say it is the opening of the control valve. Okay. C max means control valve is 100% open. C min means 0% open. Fine. And if you consider any actuator like say motor, that means it is at the 0 RPM, which is basically driving say pump. So it is at 0 RPM and C max is maximum RPM. 0 RPM is not possible at the lowest delivery level. So if you take the example of control valve, we can easily understand that this corresponds to 100% opening. This is 0% opening. Okay. Now 6th point, you see. We have the P-only controller equation. We are introducing a step change in error signal. And then we are taking inverse of Laplace transform to know the dynamic behavior. I repeat this 6th point. We have the P-only controller equation in Laplace domain. We have the P-only controller equation in Laplace domain. You see, this is the equation in Laplace domain. This is the equation in Laplace domain. C prime bar equal to Kc E bar. Now you just introduce epsilon equal to 1 by S. Introduce a unit step change in error signal. Can you tell me what should be C prime T? I repeat the question. This equation is given to you. You see the controller equation. C prime equal to Kc E epsilon. Now you consider epsilon equal to 1 by S. That means we are introducing a unit step change in error signal. Then you just take the inverse of Laplace transform and find C prime in time domain. What is the expression? Tell me.
Sir, Kc.
Yes. What's your number?
Sir, 30036.
Yes, Kc. If we consider 1 by S, C prime equal to Kc. And you see in the left hand side the graphical representation of this fact. In the left side, graphical representation of this is shown. In the first plot, we are introducing a unit step change in error signal. In time domain, it is 1. Okay. And this is the corresponding response of the P-only controller in terms of C. Fine. I hope this is clear to everyone. Now come to the next point. If Kc is very, very large, proportional controller behaves like, what is the answer? Anyone? Any answer? If Kc is very, very large, P-only controller behaves like. Okay, answer is this one. On-off controller. Fine. If Kc is very, very large, proportional controller behaves like on-off controller. See, error is either in positive direction or in negative direction. You just think that there is oscillatory response. So sometimes error is in positive side and then negative side, like that way. And if Kc is multiplied with error and Kc is very, very large, in that case, either it's completely on or completely off. It likes that. Now this is the last question. How to calculate CS? Then you will finish proportional controller. This is the last point under proportional controller. Anyone can give the answer how to calculate CS? I have indicated before although this answer. Varun Balakrishna.
When the error becomes 0.
Physically you tell me. I have one setup. Okay. You are correct, just you give the answer physically. I have one experimental setup. So I want to implement one proportional controller, but for that in my computer program, I need this CS value. How to get that? Your answer is correct, but just you need to include one physical example. You see, I told this one before. Whenever you are going to start a process, this process is not at steady state from time t equal to 0. Okay, so first you need to bring that process to steady state. And at that steady state condition, you just see what is the value of CS. Like today we have discussed one heating tank system. For that, our control manipulated variable is FST. Okay, so to get the steady state, what is the value of FST is set. That you note down. And that value is CS. Fine. After getting steady state, usually the controller is implemented. You see, I am adding one word, usually. It's not in 100% case. Sometimes, we implement the controller to speed up this startup time. I mean, to reduce the startup time. Okay. Sometimes we implement here also the controller so that the startup time gets reduced, but it's very rare case. So this is all about proportional controller. You can ask me now if you have any doubt. Otherwise, you'll go to the next controller, that is PI. Any questions, student? No. So I think you fully understood this proportional controller, and it will definitely help you to understand another a little advanced than proportional controller, that is PI controller. This is proportional and integral controller. Fine. The name suggests it includes basically two control actions. One is proportional action, another one is integral action. That's why it is PI controller. And the block diagram for this PI controller is shown in the right hand side, you see. Block diagram of PI controller is shown in the right hand side. So error is the input to both the control actions. which are in parallel, and then the outputs of both the control actions are added, and that is basically the combined output of the controller C, or maybe C prime. Fine. Now come to the equation. This is the equation of PI controller. CS is our steady state value, then proportional action is added, and additionally we have one integral action. Fine. So CS is our bias signal, then Kc epsilon, that is proportional action, and additionally we have one integral action. Now you see we have one additional term present in equation 4, that is tau y. In this PI controller we have one additional term comes into picture, that is tau y. And this tau y is called integral time constant or reset time, and its unit is time always. One additional term is present in equation 4 compared to equation 2, that is tau y, and this tau y is called integral time constant or reset time. Its unit is always time. See, I did not mention the unit of Kc because Kc depends on, from the expression delta output by delta input. Delta output, delta input, they vary from system to system. So unit of Kc is not fixed. You have to find out that. Fine. But the unit of integral time constant or reset time always fixed. It is time. It may be second, it may be minute, hour, depending on what unit you are using for your example system. Okay, unit of Kc is not fixed. It is basically delta output by delta input. So depending on the unit of output and input, you need to find out the unit of Kc. But unit of tau y is always fixed. That is time. Now in case of proportional controller, we have used alternative tuning parameter of Kc, that is proportional band. Similarly, sometimes in some softwares, instead of tau y, 1 by tau y is used as a tuning parameter. That we call as reset rate. So in some softwares, either Kc or proportional band is there as tuning parameter for P only controller. Similarly, for PI controller, sometimes this tau y or maybe 1 by tau y is used as tuning parameter. So 1 by tau y we call as reset rate. Why it is rate? Anyone? Why this 1 by tau y is called a reset rate?
So because the unit is time inverse.
Yes. Roll number?
19CH10007.
It is time inverse. That's why it is called rate. Yeah, can you find the transfer function for the PI controller? I have shown how to find out for P only.
Sir, it is Kc into tau is plus 1 upon tau is.
Tau is plus 1 upon tau is. Yes. Roll number?
19 Ch 30008.
Correct. The transfer function is like this. Anyone else got this transfer function? Shomik Sarkar 30026 or 30027 Vivek Sureka. Are you there, Vivek?
Hello.
Yeah, who is speaking?
Sir, Vivek.
So did you get this?
Hello.
Did you get this expression or no?
Yes, sir.
How? Can you elaborate this? How you got this expression?
Hello.
Okay, fine. Can you elaborate how you got this, Vivek? Okay, anyone else got this expression? Transfer function for PI student?
Yes, sir.
Good. Yeah, now we'll come to our conclusions or remarks, you can say. Like we made 8 remarks on P only controller. Similarly, we want to draw a couple of conclusions on this PI controller. First one, you see, it is basically the combination of two actions. One is proportional action, another one is integral action. So we can draw our conclusions separately also. Few conclusions are specific to proportional and few are integral. Or sometimes in combined form also we can conclude if there is something. Okay. Now this first remark, it is specific to proportional action, you see. Proportional action speeds up the response of the closed loop process. I have shown graphically that if we increase the Kc value, we get faster response, but definitely at the expense of higher oscillation. And in fact, longer oscillations and higher deviations. First comment is specific to proportional action. Let me repeat this. PI controller is basically the combination of two actions, proportional and integral. So we can draw few conclusions separately for proportional and integral action. Okay, and sometimes also we can draw few conclusions in combined PI form. So this first remark is specific to the proportional action. It speeds up the response of the closed loop process. In fact, I have shown graphically that with the increase of Kc, we get faster response or speed of response increases, but at the expense of higher deviations and longer oscillations. This is for proportional action. Second point is specific to integral action. You need to note down this point. Integral action eliminates the offset. You remember this term, eliminates. It does not reduce, it completely eliminates. I repeat, integral action eliminates the offset. Eliminates, this word is very important. You cannot say reduces the offset. It's wrong if you write reduces. I'll show you later. Fine. It completely eliminates. If it reduces, then your tuning parameter set is not correct. You have to change them. Then one sentence is written there, you see, as long as the error is present, the PI controller keeps changing its output by integrating the error signal. Fine. Integral action completely eliminates the offset. And this is the reason. As long as the error is present, the PI controller keeps changing its output by integrating the errors. So I will show you a little later, maybe in the next class, how it happens. And offset, I have already shown you what is the concept of offset. You see, it's the steady state error. After a certain period of time, this error does not change with time. So this is called offset. Steady state error. That means after a certain period of time, this error does not change with time. That is offset. Next point is quite interesting, you see. If we add integral action with proportional action, the overall response becomes more sluggish. If we add integral action with proportional action, the response becomes sluggish. I mean, if you do not consider integral action, if you use only proportional action, you will have faster response. But if you just add integral action with P, you will see that your response is becoming sluggish. Now, question is why? You see, this is the answer for P only controller. This is the answer of P for PI controller. Suppose we have a first order process. We are adding P only controller. Then there is no change of order. We have first order process, we have PI controller. The order has increased by 1. We have first order process, we are employing P only controller. The closed loop process order does not change. But we have first order process, we are employing PI controller. The order has increased by 1. And you know, I have shown graphically before, the change of order leads to make the system sluggish. Okay. So you remember this point, proportional controller speeds up the response. Integral action eliminates the offset. That's why we are very eager to include integral action with P. But as soon as we include the integral action with P, our overall response becomes sluggish. Fine. Now come to this point. The similar response we have observed for proportional action as well. This is the fourth point, you see. If we increase the integral action, we get faster response, but at the expense of increased oscillations. If we increase the integral action, that means reducing tau I, because if you recall, the PI controller equation, tau I is present in the denominator. Kc is present in the numerator, but tau I is present in the denominator. That's why if we reduce tau I, it leads to increase the integral action. I repeat, tau I is present in the denominator in PI controller equation. Therefore, if we reduce tau I, it leads to increase the integral action. So if we reduce the integral action, we get more oscillation, but faster response. So can you recall the similar plot I have shown with respect to Kc? What is the difference between this plot and that plot? I repeat my question. This plot is shown for the change of tau I. If we reduce the tau I, we get faster response, but at the expense of increased oscillation. Similar plot I have shown for varying Kc value. What is the difference between this plot and that plot? Anyone?
Offset.
Yes, correct. What's your number?
30001.
Offset is the difference, you see. So it is also mentioned that integral action eliminates the offset. Okay, that's why it is indicated here. Integral action eliminates the offset. I have mentioned before. That's why offset is not included in case of y versus t plot with reference to tau y. Yeah, next point is this one. We have a PI controller equation. I am showing you again. This is the controller equation in Laplace domain. Now we want to introduce a unit step change in error signal. Then take the inverse of Laplace transform and let me know the expression of C prime. A similar problem we have solved for proportional controller as well. I repeat the question. This is the controller equation, PI controller equation in Laplace domain. You introduce a unit step change in error signal, epsilon. And then take the inverse of Laplace transform and let me know the expression for C prime. Do it quickly and let me know the answer. Expression for C prime in time domain.
Kc into 1 plus t by tau I.
Kc into 1 plus t by tau I. Yes, correct. Roll number?
19CH10061.
Tridipta Das. Anyone else got this expression?
Yes, sir.
What is the expression? Tell.
Sir, it is Kc into 1 plus t by tau I.
Yes, correct. You see, this is the answer. Agree? Now the plot is shown in the left hand side. You see corresponding plot we have also developed for P only. And this is drawn for PI controller as well. In the first plot, it is shown that the error signal is, a unit step change introduced in error signal. This is the first plot. And in the middle plot, C versus time t. And in the third plot, C prime versus time t. Okay, I think you are understanding the plot. There is no difficulty at all. The graphical representation of CT against a unit step change in error signal. So it basically includes a step function or a step change. Another one is the ramp change. Okay. And C prime t is quite obvious. CS will not be present here. That's the point. Because C prime t itself includes CS term. Clear? Any doubt? No. Okay. Now come to the next point. How to define the reset time tau y. See, I have already clearly mentioned or detailed about proportional gain Kc. We have talked about CS bias signal, but we did not explain this tau y in details. Now we want to extract the definition of this tau y. I repeat, the controller equation basically includes CS bias signal that is explained in detail. We have Kc in the controller equation, proportional gain, that is also detailed. We have another term tau y, reset time, that is not detailed so far. That is not explained in detail so far. Now we want to explain that tau y. What is this? See, this is the equation just now we got. This is the PI controller equation in time domain we just got. Fine. Now what we want to do, we want to substitute this t by tau y. We just want to substitute this t by tau y. And you see, the integral part corresponds to Kc. We are substituting t by tau y. We are replacing t by tau y. Then the integral part yields the term Kc, which is same with the proportional action. which is same with the term provided by the proportional action. Can we extract now the definition of tau I? Can anyone extract the definition of tau I based on this discussion, student? What is reset time?
At reset time, the proportional action and integral action becomes equal.
Yes, that is obvious. So let us write in this way. You see the definition for reset time? Fine, I think it is quite obvious. Reset time is the time needed by the controller to repeat the initial proportional action change. Initial means that is provided by the proportional action in its output. But this is true against a unit step change in error signal. Okay, so this is the formal, this is the definition, you can say. This is the definition of reset time, which is extracted from this discussion, from this mathematical representation. And it is obvious, it is true when we consider a unit step change in error signal. Okay. Now this is all about PI controller. Is this clear to everyone, or do you have any question? This is all about PI controller. And you note down this question and give me the answer in the next class coming Thursday. Note down this question, solve it, and let me know the answer in the next class. So this question came in your semester exam 2017. And this question came in GATE exam in 2016. Now question is this one. Find the values of Kc and tau I. Okay, so you can let me know the answer in the next class. So this is all about today. Thank you to everyone.
Thank you, sir.
Thank you, sir.
Thank you to everyone.